Hello students, good evening. Today we'll discuss our first part of work power energy. Now when we talk about this word work, you definitely know that work is nothing but force into displacement. This you know from your previous class. Now we need to understand that displacement should be in the direction of the force. Let us explain. If you have a body of mass m, if you apply a force here F, which is acting at an angle theta, and the body is translated till this distance, say this is S, then if this is the force, this is the displacement S, and the angle between force and the displacement is theta, then the work, we cannot multiply just F and S. What we have to do? We have to take the component of F in the direction of S. So this will be, as this is theta, this is F cos theta, and then we need to multiply the force and the displacement. So the work done, we can write F into S cos theta. We can also imagine the displacement to be in the direction of the force. Like if we think that this is the force, we can, if we take the component of the displacement in this direction, then also we can reach the same equation. So as work equal to Fs cos theta, we can combine it, in terms of vector, as force and displacement both are vector, we can write it as dot product of F into S. Now let us illustrate on this angle theta. If angle theta, this angle between the work and the displacement, if it is 0 degree, what does this mean? It means the force and the displacement, they are in the same direction. Then what will happen? The work will be nothing but F into S. Definitely it is the maximum value of the work which is achievable. And you can see the value is positive. What is example? Anything like any force which is moving a body in a particular direction. Suppose a ball which is falling under gravity, the weight of the body, mass into gravity, and the distance and the displacement, they are in the same direction. So definitely this work is a positive work where the angle is also 0. Now what is theta? Is say 180 degree. If theta is 180 degree, then what we understand? That is the force and the displacement, they are at an angle of 180 degree, that is they are opposite to each other. Now when opposite to each other, when angle is 180, cos 180 is minus 1. So work will be nothing but Fs cos 180, that is minus F into S. Now, minus means it is a negative work. Let us illustrate with the next example. Now the same example that we have described. Now when a body, if it is thrown in the upward direction, then if you observe, what is the work done by the force of gravity? The force of gravity is in the downward direction, but the body is moving in the upward direction. The displacement of the body and the force, they are at an angle of 180 degree. So definitely in this case, the work is negative. Okay. Now we come to the third part. Theta is when 90 degree. Now you definitely know that cos of 90 equal to 0. So what will be the work? Work is also F into S into cos of 90, that is 0. Now when it is 90, it means the force and the displacement, they are perpendicular to one another. What can be the example? A very simple and very common example is, and you know this, that is when a body moves in a uniform circular motion. When a body moves in a uniform circular motion, you know that at every point the displacement is tangential, whereas the force is directed towards the center, which is called the centripetal force. So in this kind of uniform circular motion, you can see, and as it is coming in a round path, you you try to explain it in your initially when we don't understand this one, or when we don't know this equation, we used to say what? As a displacement is 0, the work is 0. It's not that. As in a uniform circular motion, at every point the work done is 0, because the work is done by the centripetal force and the displacement is tangential, which is always perpendicular, and you will see F is cos of 90, so it is 0. There is another very good example of this. Like if I say a coolie is carrying some load on his head and he's walking. Now the question is, what is the work done by the man? What is the work done by the force of gravity? By the force of gravity when the man is walking like this. See, the work done by the force of gravity, in this case the force of gravity is mg, is in downward direction. The man is walking horizontally, so this is the displacement. So definitely the angle between the displacement and the force is 90 degree. So the work done, work by force of gravity will be 0. So you can think, so isn't the man not doing any work? Yes, the man is definitely doing a work, but that is not being contributed by the force of gravity. The man is walking on the road and the road is having friction, and you know the friction opposes the motion. So man is actually doing the work, or the work is being done by the force of friction, and the displacement is in the opposite direction. So we can say force of friction into this displacement, then we are calculating the work. But the work done by the force of gravity is 0. Okay. Now we are talking about, constant forces. That is when the work is done by constant forces. Now what happens when work is done by forces which are variable? Work done by variable forces. Now when the force itself is variable, then we cannot find out the work just by simply multiplying force into displacement. We are not considering the angle for the time being. So what we can think, let us consider a very small displacement. Let us consider a very small displacement dx, on which the force is constant. Now, for a very small displacement dx, when the force is constant, we can calculate a very small work, that is nothing but F into dx. And this force is a variable force which is actually varying with displacement. So F is actually a function of x. So if we want to find out the work done, we are doing nothing but the integration of F dot dx. And if x is varying from, say, x1 to x2, so we can do like this. What does it represent actually in graph or in graphical form? As we have already discussed, that force is a function of x. So if we plot force in the y-axis and x in the x-axis, definitely, if the way the force varies is a random function, suppose it's like this, so we can think if this is dx, very small dx, and this is the general f, so we are actually finding f dot dx means the area of this very small, this thin rectangle. So when we integrate it from x1 to x2, say this is x1 and this is x2, we are actually finding the area under the curve. So work done, we can say area under curve force against the displacement. Okay, now all these forces we are talking about, there are two kinds of forces. One is the conservative force and one is the non-conservative force. We'll come one by one. What are conservative forces? Conservative forces, as you know, like gravitational force, elastic force in spring, or electrostatic force, all these are conservative forces. We will see. Conservative forces means basically the work done which doesn't lead to any loss of energy, where energy remains constant, but where there is no loss of energy. Energy remains constant in both kind of forces, conservative as well as non-conservative forces. But here there is no loss of energy. The work done is completely transferred to kinetic energy. We'll discuss it. Let us try to think what is the work done in conservative forces. In conservative forces, you will see, say there's a point A, there's a point B. We are taking a body from point A to B in several different paths. This is path 1, this is path 2, this is path 3. We will see the work done in any path remains the same. It means what? That is, work is independent of path chosen. In terms of calculus, we can say if these are the path and the length of the path is L, the line integral of force and the path will be same in all the cases. That is basically the work done AB through 1 will be equals to work done AB through 2, work done AB through 3. Whatever be the path, the work done will be constant and it is independent of the path taken. It only depends on the initial and the final point. Let us illustrate what I said. Gravitational force is a conservative force. Let us see whether we actually draw this conclusion. Say this is a mass m. It is taken to a height h. What is the work done? It is mg. The height is h. Ignoring the sign for the time being, we can say work is nothing but force means mg into the displacement, that is height h. Now this is one way we have done it. Another way, say this body is taken in a different path, not the body is taken in a different path, not in this vertical way. Say this path is at an angle of theta with the horizontal. Now let us try to find out this work done. Now when we take the body like this, the force is in this direction. So we need to definitely calculate the force in the direction of the displacement. Displacement is this. Now, if you see, so we have to calculate the force in this direction. So this, if we draw this perpendicular, if this is theta, this is also theta, this is also theta, then definitely this is mg. So this will be mg sine theta. So the force in the force component in the direction of the displacement is mg sine theta. Now this is h. Now we are taking the body from this point to this point, that is, this is L, this length L. Now what is the length L in terms of h? You can see h is nothing but L of sine theta. So L equals to h by sine theta. Now what is the work done? Work done is, force in this component is what? mg sine theta into L, displacement mg sine theta into h by sine theta, that is, sorry, mg h. So, and if we can go for other paths also, we can see the same result. So gravitational force, we can definitely say it is a conservative force, where the work done does not depend on the path we choose. It depends just on the initial and the final position. Initial and the final position. This is the first position. Here also, I mean, if we take this as a second position, it depends only on the positions. Okay. Another conservative force is the spring. Elastic force we will discuss now. We will try to find out what is the work done for in a spring. In a spring, you know, when we stretch the spring, there is a force which is generated within the spring, which is called the restoring force. And this restoring force F is actually proportional to the displacement or to the extension. Proportional to the extension. And you will see, as it is a restoring force, means the force is actually directed opposite to the displacement. So force, we can write F equal to minus kx. We will calculate the work done for a spring for a displacement of x. Say, now here also force, you can see, is it's a function of x. So definitely it's a variable force. So to calculate work done, we need to use integration. dw equals to f dx, that is minus kx dx. If it is extended from x1 to x2, you can find kx square by 2. This is x1, x2 minus, that is, if you put this is x2, it will be k by 2 x1 square x2 square. By this way we can find out the work done in a spring, and you will see this spring elastic force is also a conservative force. Electrostatic force, electromagnetic force, all these are conservative force system. Now what are non-conservative force? It is evident from the word non-conservative, means it is not conserving the energy, that is the work done, the energy, some energy is getting lost. All kind of friction viscous force, viscous drag, anything, surface tension, all these forces are all non-conservative forces. Let us say friction. Say the coefficient of friction is mu. Friction, you know, it opposes the motion. Friction, it opposes the motion. So the friction is mu mg. If you take a body through a path which is having friction, then this work done, we cannot get it back. It is lost at some heat energy, or we cannot conserve it, or it will not translate into its kinetic or potential energy. And for non-conservative forces, it does not, it does depend on the path. That is, so the in this case, the work done is dependent on path. Another thing, in the case of conservative force, we can easily deduce that if a body moves from this point to this point, A to B, and then again comes back from B to A, the total work done will be 0. That is, for a closed loop, the work done will be 0 for a conservative force, because as it is not dependent on the path. So what happens? If I say WAB and this is WBA, definitely WBA will be negative of WAB, which we cannot say in case of non-conservative force. So we learn two things. One is, for conservative forces, work done is independent of the path, whereas in the case of non-conservative forces, work done is dependent on the path. And in a closed loop, for a conservative force, the work done is 0, whereas in the case of non-conservative force, work done we cannot say like this. And the concept of potential energy we'll discuss is only related with conservative forces. It is not related with non-conservative forces. We are coming to energy now. The energy, capacity of doing work, there are numerous forms of energy. Here we'll basically deal with mechanical energy. And in mechanical energy, one is kinetic energy, one is the potential energy. Now, the formula kinetic energy equal to half mv square. But how do we deduce that? From where do we get this? Kinetic energy equals to half mv square. See a body whose initial velocity is 0. That is, the body is at rest. It is a constant force F is applied on the body. The body is having a mass m. So the constant force will be producing an acceleration a, where F will be equals to m into a, and it will move through a distance. Suppose for this constant force, the body moves through a distance of x, and it achieves a velocity, a final velocity of v. Now from the third equations of motion, v square equals to u square plus twice as, here s equals to x, so u square plus twice ax. Now, u is 0, so v square equals to 2ax. Now, yes, so we can find x, the displacement in terms of v square, that is v square by 2a. Now the force F equals to ma, so the work done will be F into displacement, that is mass into acceleration into v square by 2a, that is a will cancel out, it becomes half mv squared. Now you can think in this way: as a body was initially at rest when force was applied, and it has the body and the work and the force has done a work which is equal to F into x, the work has been completely converted into the kinetic energy of the body. See, the body is at the same level, so no other form of mechanical energy like the potential energy is we are we don't have any potential energy here. So only energy in which the work is getting translated is the kinetic energy. Then definitely the kinetic energy of the body should be half mv squared. We can relate this thing into another important concept called the WorkEnergy Theorem, which says that work done by any force, by all forces, conservative, non-conservative, everything, if there is no loss occurred during the work, the whole of the work done gets converted into the kinetic energy of the body. That is, the total work gets converted into the kinetic energy. So if Kf is the final kinetic energy and Ki is the initial kinetic energy, the change in kinetic energy is nothing but the work done. We can see like this: say a body is moving with a velocity u. With similar approach, the final velocity reached is v upon a distance of x. So definitely we can write v square equals to u square plus twice ax. So ax is nothing but v square minus u square by twice a. F is nothing but m into a. So work is m into a into x, that is ma into half, if you a cancels out, is m by 2 v square minus u square. If you, it is half mv square minus half mu square. So half mv square is the final kinetic energy of the body and half mu square is the initial kinetic energy of the body. The work is getting translated into the change in kinetic energy. Now what is potential energy? This you know, the energy possessed by virtue of its position, and also for position or for compression in a for position it is called the gravitational potential energy. For elastic potential energy that we get in springs. In general, we define potential energy, this concept is only associated with conservative force system. And in this, we define potential energy to be negative of work done. Let us try to illustrate. For gravitational potential energy, say when a body is raised to a height of h, we know this is mg, the weight of the body, height is h. If you consider the direction in this case, the mg, the weight of the body, and the displacement, they are in the opposite direction. So the work is nothing but minus mg into h. So the potential energy equals to minus w, that is mgh. Let us try to get the elastic potential energy here. Displacement x. So dw equals to minus f dx, sorry, it's minus kx dx. So work is nothing but, if we integrate, it will it is minus kx square by 2. So work done equal to minus kx square by 2. So if I write what will be the potential energy stored, it is nothing but negative of work done, which is half kx square. So this is the potential energy stored within a spring when it is stretched through a distance of, or the elongation is x. Now let us come to the last topic, which is power. Power, you know, it is nothing but rate of doing work, rate is nothing but is dw by dt in terms of calculus. So it is ddt of r. Let us consider the force is constant. If force is constant, it will be dr dt. Let's make it vectors also. We know dr dt is nothing but velocity. So for a constant force, power can be written as the dot product of force into velocity. Okay, let us solve some problems to understand these concepts. Let us see how we can apply this formula into some problems. Let us see the first problem. When a rubber band is stretched by a distance x, it exerts a restoring force of magnitude F equals to ax plus bx squared, where a and b are constant. The work done in stretching the unstretched rubber band by L, so L is the elongation. This is a very direct question. Force is ax plus bx squared and the total stretching is L. Now force is itself a function of x. So we have to, for calculation of work done, we have to write work equals to, that is integration of f into dx, and the limit will be from 0 to L. This is ax bx squared. It will be nothing but 0 to L ax squared by 2. This will be bx squared by 3. It will be nothing but al squared by 2. It will be this one. This is a very direct question. Let us see the second question. An object of mass m is tied to a string of length L. Means object of mass m tied to a string of length L, and a variable force F is applied on it. A variable force F is applied on it, which brings a string gradually at an angle theta with the vertical. Find the work done by the force. Now, this is a good question. Let us try to analyze this. I'm keeping the question here so that you can also see. An object of mass m is tied to a string of length L, and a variable force is applied on it which brings the string gradually at an angle of theta with the vertical. Okay. Now the force given is a variable force. So we cannot directly apply, or we don't know how the force is also varying. For this kind of problem, we need the concept of conservation of energy. That is, work done getting converted to energy, to getting converted to potential or kinetic energy. See, this point, the body is at rest. Here also, the body is at rest. So there is no question of kinetic energy. Now, what happens when a body is moving through a height? Its potential energy is elevated. When its potential energy is increased, but kinetic energy is 0. So definitely it is being done by this force. So the work done is nothing but the increase in potential energy in this case. Okay. Now what is the increase in potential energy? This is L. This angle is theta. So this length will be L of cos theta. So how much distance this ball has actually risen? It is nothing but this. So this is L minus L cos theta. So which is so the rise in potential energy is mg L1 minus cos theta, and this rise in potential energy is being contributed by the force, by the variable force, because there is no other force acting on the body. Okay, now let's come to the second problem. Okay. A cord is used to lower vertically a block of mass m by a distance d with a constant downward acceleration g by 4. A cord is used to lower vertically a block of mass m by a distance d with a constant downward acceleration g by 4. Now, if you remember the concept of pseudo force, when the mass is going down in acceleration g by 4, there must be a pseudo acceleration acting on the body in the upward direction g by 4. So the pseudo force is mg by 4. So what is the net force acting on the body? It's mg minus mg by 4, that is 3 mg by 4. The net force acting on the body is in the downward direction. Now what would be the work done? Is nothing but the net force into the distance. So work done is nothing but 3 mg by 4. A cord is used to lower vertically a block of mass m by a distance d with a constant downward acceleration. The net force is in the downward direction. The displacement is in the downward direction. So it will be B. The answer is B. Okay. Next question. A particle is acted upon by a constant power. Then which of the following physical quantity remains constant? Now power is constant means we can say force into velocity is constant, but the product of force into velocity is constant, but we don't know whether force or velocity or both are varying. Now let us try to see. Speed we cannot say. Rate of change of acceleration, that we also cannot say. Kinetic energy we cannot say, because if velocity is varying, kinetic energy can also vary. Now what is rate of change of kinetic energy? Rate of change of kinetic energy, we can say it's rate of change of work done, and rate of change of work done is nothing but power. So when power is constant, it means rate of change of kinetic energy, it is also constant. The answer is D. This kind of small questions you will get in joint interest main. I'll discuss one more final question which needs more solution. Okay. A point particle of mass m moves along the uniformly rough track PQR. I'll draw it once more. A point particle of mass m moves along the uniformly rough track PQR. As shown in the diagram. The coefficient of friction is mu. So it is given between the block and the whole path. Mu is the coefficient of friction. The particle is released from rest from P. The particle is at rest at P and comes again to rest at point R. So when it is reaching point R, then also it is at rest. The energy is lost by the ball over the paths PQ and QR of the track are equal to one another. The energy which is lost between PQ and QR, they are constant. And no energy is lost when particle changes direction from PQ to QR. We have to find the values of mu and the distance x between Q and R. Now, there are 2 points we need to note. First, the particle is released from rest and it is also again at rest at point R. If you try to analyze the whole problem, the body at height h, this height h is given 2 meter. The body at height h is definitely having potential energy. Now, in general, if there wouldn't have been friction, so what would have happened? When the body will fall down, it will lose its potential energy and it will increase the kinetic energy of the body. But as the whole path is having friction, then what is happening? The potential energy, that is the gain in kinetic energy, the kinetic energy is also getting lost because it needs to do some work against the force of friction. So finally, as the kinetic energy of the body at point P and the kinetic energy of the body at point R, the initial and the final point, is 0, we can definitely say the change in potential energy is actually contributed the work done by friction. Now, what are the frictional forces? How they are taking part in these two paths, PQ and QR. Let us consider first PQ. When a mass m is like this angle theta is given 30 degree. This is mg. This force towards the plank is mg cos of 30, mg cos of 30. So the frictional force, the opposite direction, friction, let this friction be friction 1 and this friction be friction 2. So Fr1 we can write, if this is mg cos 30, it is mu mg cos 30. And so what is the loss in energy for this part? This is mu mg cos 30 into this distance. Now this distance you can find out as this is 30, this height is 2 meter. So this will be nothing but h by cos 30, that is this will be 4 meter. So mu mg cos 30 into 4. Now let us find out what is the work done at this point. At this point, what is the frictional force acting? It is moving on a horizontal. So definitely this force is mg, the friction will be mu mg. So work done mu mg cos 30 into 4 will be equals to mu mg into x. So now you see this work done, it is given the energy lost by the ball over the parts PQ and QR of the track are equal to each other. It means definitely the energy lost at PQ equals to mu mg cos 30 into 4 must be equals to mu mg into x. So here mu mg part cancels out. So x will become 4 cos 30 equals to root 3 by 2. That is 2 root 3. If you calculate 2 root 3, 2 into 1.7, it will nearly come to 3.5 meter. Now let us try to find out what is mu. For mu, there is another point we need to remember. The total potential energy is distributed, is nothing but the work done in the whole path. So PE is nothing but mg into 2m, that will be equals to mu mg cos 30 into 4, this plus this. So it is mu mg cos 30 into 4 plus mu mgx. Just in the previous equation we have seen this will be equal to this, so we can write 2 mu mg cos 30 into 4. Now we have to find out the value of mu. It is 2 mg. So mg cancels out, 2 cancels out. So mu we can write, so mu is nothing but 1 by 4 cos 30, that is nothing but I'll write like this, 1 will be equals to mu into root 3 by 2, 2 root 3. So mu equals to 1 by 2 root 3. If you find out, its value is 0.29. So the answer will be 0.29 and 3.5 meter. You will get a lot of questions from this topic. Solve the problems and I'll meet you in the next video with the next topic of work power energy. Thank you.